Okay. Hi everyone. Last session we talked about decision tree learning. We started with actually a definition of like classification and how we can actually build a decision tree based on the data that we have. And so we discussed a few issues when we want to build a tree based on the data. So anyone remember what was the main issues? Let's say you want to create a tree based on this example. Yes.
Choosing the internal nodes, like which features to choose as the nodes.
Yep. So that is one issue. So finding which attribute we have to start with. So for example, here we have outlook, temperature, humidity, and wind, which are attributes or candidate attributes to be selected as the root node. And then we have our class label yes and no for playing tennis. So based on the weather conditions, we want to decide whether the weather is suitable for playing tennis or not. And now there were several ways to build a decision tree based on this data. We can start, for example, with outlook and then say, okay, the outlook could be sunny, overcast, or rainy. And then, for example, let's go to the branch of outlook sunny. Then what should be decided next? Should we test it on humidity or wind or temperature? So that is one of the issues or one of the challenges in decision trees, because we have to select which feature is best to, which feature, if we choose, can best partition our data. And how can we say that which feature is best? How to decide that best feature? So for example, if you have an attribute, and let's say in that attribute we have 10 tuples, we have 10 rows, and let's say 8 of them or 9 of them belong to class yes, 1 or 2 belong to class no, right? Now in this case, if we have 80% of our data belong to one class and like 10 or 20% belonging to the other class, is it a good split? Is it pure? So how do we define the purity? When all our examples or instances of data belong to the same class. Okay, why? Because let's imagine if all your data belongs to, for example, here in the overcast, if the outlook is overcast, what would be the outcome? What would be the result? So what are the class labels for outlook overcast here? So for the outlook overcast, if you see, it's always yes, right? So how many instances of overcast you have? 1, 2, 3, 4. So all 4 of the overcast instances belong to the class label yes. So do we need to further branch out this attribute here? No. Because so all of them belong to the same class. So we can say that, okay, if the outlook is overcast, so you can definitely go to play tennis. What about the other features? Are they like, can we say they classify like, lead to like a pure split? For example, if the outlook is sunny, can we say it's ideal for playing tennis only based on outlook sunny?
No.
Because some of them are yes, some of them are no. So not all the instances belong to the same class. Now, this is how we measure the purity, right? So if we have all instances belonging to the same class, it means that it's pure, it's the purest. And in that case, the entropy is 0. And how did we calculate entropy? We said, okay, it's entropy of a set, let's say set S, is probability of an instance belonging to class Ci, right? And we multiply it by its log. Now, we said that if all instances belong to the same class label, is purest and the entropy is 0. So why entropy is 0? Because this is the probability that an instance belongs to for example, class 1, let's say, okay? And let's say we have like 2 just classes, and PC1 is 1 because the probability is 100%, right? And when PC is 1, so the result of the log would be 0, right? Because log of 1, right, would be 0. 2 to the power of 0 is 1, right? So when it becomes 0, so the entropy is 0. So when our data is the purest, or when the probability of instances being in the same class, we have that situation, then the entropy is 0. And when the entropy is going to be maximum,
is 1.
when we have like less, exactly. So it's, let's say 50% of data belong to 50% of our tuples or our instances belong to one class, and 50 half of it belong to, let's say, class yes, half belong to class no, right? In that case, we have to calculate the log of right, and this is -1. So that was for calculating the entropy. So why are we computing the entropy at all? So why do we need the purity? Because we want to decide which feature to choose as the root node, or like later when we want to further continue like branching out our tree, we want to select the best feature. And we said that the best feature is the one that can best split the tree, and the best split is when the result of our split is that most data, or like all of them, belongs to the same class. So that's why we need to calculate the entropy. So keep this example in mind, and then I'm just going to review with you. Just this is an example, and also and then next, based on the entropy that we calculated, we said now there are several methods that give you the best attribute. In this class we're discussing 3 of them. One is information gain, which we covered last week, and there are 2 other methods which are almost similar. So back to the information gain. Do you remember how information gain could help us to select the best attribute? Yeah, so the highest information gain. So we calculate the information gain based on the entropy, and the highest information, the attribute that gives us the highest information gain is the one that we select as the best attribute. And so let me get back to the information gain here. So look at the formula of the information gain. So gain of a set, let's say a set of S, with respect to the attribute A, for example, if your attribute is outlook, is entropy of S, which is you're calculating the entropy for the whole set, minus the weighted sum of the entropies of our like subsets, right? So Si is a subset of S. For example, if our set includes several features, Si could be like the subset of that. Now, if for example, A is the outlook in our example, if A is outlook, what would be M? So what are the possible values of outlook? The possible values of outlook are, yep, so M is 3, right? We have 3 attributes. So that is M in that formula. So you have to calculate the weighted sum of the entropies for those subsets. For example, what do I mean by subset here? So for example, subset could be if the outlook is sunny, if the outlook is, for example, rainy, right? And so on. So that will be your information gain. So for the information gain to be the highest, what does that mean? What is the relationship with the entropy? So the less is the entropy, right? The less is the entropy is the highest information gain. So and here in this formula, when you calculate the gain of your set with respect to an attribute, so can you tell me, based on this, what you see here, let's say if we want to, if I select the outlook, if I say A is outlook, so I select this feature. And we said M would be 3 because outlook could be sunny, could be rainy, or could be overcast, right? Now, what would be the gain of S with respect to the output? What should we calculate for this one?
The entropy of the whole tree first minus the entropy of output.
So entropy of S minus the weighted sum, right, of entropies of the subset. Yeah. And then we have this sigma here. So this sigma means that when we are partitioning, so we have to sum the entropies for all of the branches, right? So for example, if the branches are, this is outlook, are sunny, overcast, and rainy, so we calculate the entropy for this one, and for this one, right? So we calculate the entropy of S with respect to all the subsets. Now, let's go to this example. We want to select what attribute is best for the root. So we have to check all the attributes. What are the candidate attributes in this data? Look at your table. So the candidate attributes are outlook, humidity, wind, right? Because you have this table, you have outlook, you have wind, you have temperature, and so on. And then you have your class labels here, which is play or not. Now let's say yes, no, no, yes. So you have this. So these are your candidate features. So you can start your tree with any of these features, right? And to predict the class labels, to predict whether you want to play tennis or not. And okay, now, which feature to select? In order to understand which feature to select, you have to calculate the entropy, which I explained before. And so in this example, we have to calculate everything for all the attributes we have. For the humidity, we check the information gain for the humidity. We check the information gain for the outlook. So for all of them. So outlook, humidity, wind, temperature. So we want to decide which of these 4 attributes will be your root node, right? For that, so first of all, you have to calculate the entropy of the whole set, which we did before. And then, so for now, each of these, I'm going to find the entropy with respect to selecting this attribute. Because if we want to see if we select this attribute, what would be the impact, right? How does it, what would be the purity of our split? How does it partition our data? So in our data set, we have 14 days, and how many belong to class yes? 9, and 5 belong to class no, right? So you need to understand this, you need to see the table. So you have to go back to the table, this one. So we had 14 days here, D1 to D14. Out of these 14 days, 9 of them belong to class yes, 5 of them belong to class no. So S 9 plus and 5 minus means 9 belong to class yes, 5 belongs to class no. And then we also calculate the entropy for the whole set using that formula. So the probability of instances belonging to class yes and no. So for example, here we had 9 minus 9, 15 multiplied by log and 5, 14, sorry, because we have 14 days by the log of 514. So the result of this calculation would be that number. So that number is 0.940. Okay, now we know the entropy of the whole set. And what are the outcomes of Outlook? So we call Outlook here a test. We are doing a test on the Outlook. We want to see, for example, what are, sorry, here is the humidity. I'm really sorry. For the humidity, we want to see what are the outcomes of humidity. So the humidity in your table, what are the possible values? Those are your outcomes. So these are for humidity. Okay, humidity could be high, or what was the other? Is it normal or low? Yeah. So humidity could be high or normal. And now you have to calculate the same thing for all the subsets. So for example, you say, what would be the S of humidity high? So let's say S of high. So how many of your data in humidity high belongs to class yes? How many belongs to class no? So back to the table, go back to the table here. So look at the humidity. So for the humidity high, D1, D2, D3, D4, D8, D12, and D14 are high, right? So how many high? How many high do we have? 7. So we have 7 humidity high. Out of these 7 humidity high, how many of them belong to class yes? So humidity high, 1, 2, yep, 3 of them belong to class yes. So we have S high, 3 plus. How many belong to class no? 4. 4 no. So that's the meaning of this. Again, for humidity normal, how many belong to humidity normal? It should be 5, I guess. Because there are 14, 7 are humidity high. 7. Oh, 7, yep. So for these 7, how many of these humidity normal belongs to class yes? So we have 6 plus and 1 minus. Now we have to calculate entropy for each of these branches, for each subset, okay? Now I say, okay, what would be the entropy of S high? We calculated that based on the same formula that we did it here. So we say the probability of being in class yes and probability of being in class no. So 3, 7, and this number is 0.985. Yep. Now we do the same for humidity normal. So in that case, the entropy is 0.592. How do we calculate the information gain here? So the information gain is calculated based on the actually reduction in the amount of entropies before and after partitioning, okay? So what was the entropy before partitioning? It's entropy S, right? Entropy S at the very beginning is when we say, okay, 9, for example, 9 instances belong to class yes, and 5 instances belong to class no, and we calculated entropy. So this calculation was based on the whole set of data, right? Am I clear? Okay. So this was based on the whole data. Now we want to see how much we reduce this entropy based on our partitioning. So we have to find the difference between this entropy and the entropy based on our partitioning, right? So what is the entropy based on our partitioning on humidity? So it is the entropy of whole set minus what would be the entropy of humidity, the weighted sum of entropies for each branch, right? The entropy if humidity is high and the entropy if the humidity is low. So that is your information gain. So you reduce the entropy of S with the weighted sum of the entropies of each branch. And we repeated the same process for all the features. So I repeated this for all the features. So as you can see, for all of them, we started with the whole set. So we calculated the entropy before partitioning, before splitting with the whole set, which was 0.940. And then we went to all the possible outcomes of each feature and calculated the entropy for each of them. For example, calculate entropy for outlook sunny, for overcast and rainy. And then the information gain for the outlook feature would be the entropy of the whole set minus the weighted sum of the entropies of each of these branches of outlook, which are minus entropy of sunny, minus entropy of outlook, overcast, and rainy. What about for wind? Can someone explain me how does this, whatever I explained, I just want someone to describe it for example, feature wind. How did we calculate the information gain if we select the attribute wind? Any volunteer? Yep.
So the entropy is the same because you're calculating the entropy for the entire set, right? And then you're just subtracting the weighted sum after you partition the data based on the wind class.
So what entropy is the same for all?
So the entropy is the same for the entire set.
Yeah, so the entropy of it.
You're subtracting the new entropy from.
Exactly. So you find the new entropies after partitioning, sum them, and then deduct it from the entropy before partitioning. So to find how the entropy has changed. And why we do that? Because entropy, as we said, was a measurement for randomness or impurity in data, right? And so we repeat this for all the features to see which feature gives us the highest information gain. So the highest information gain, the attributes with the highest information gain is selected as the root node. So we found where we should start from. So we start from Outlook. Now, which feature should I select next? For example, let's say, okay, if the Outlook is overcast, we reach to the leaf. What were the conditions of reaching to the leaf or declaring a terminal node in a decision tree? When do you find that you have reached to the leaf? Yeah.
So when all of them are categorized in one category?
Yeah, so when all instances belong to the same class, that's one condition. Or, so this is the case here, because in overcast, we have 4 instances in our 14 days that the weather, we have outlook as overcast, and all of them are yes. So why should we go further? So we can already have a rule for classification. We can classify. We can say, okay, if outlook is overcast, then play tennis. Go play tennis. And now there are other conditions to declare a node terminal. For example, let's say if you are, for example, branching out your trees, so you have, for example, some node here, and then you come here, and something like this. Now, another situation that you reach to the that you declare a node as a leaf node, or you say that okay, we reach to the leaf, is when you have no more attribute to put as your like a splitting attribute, right? So we have a limited number of attributes in our data set. So for example, we have 5 attributes. We have 4. For example, here we had 4. So if we are already like use all, then we have no. Yep.
Is it possible to get to all? For example, like you reach to a point that every leaf has like entropy 0, which like shows is pure. So that's gonna be the leaf. But like afterwards, when we like get all the leaves as like purity 0, we still have like attributes left. Is that possible?
After we reach the entropy of 0.
So basically, we go through the nodes and we're like doing it like with the steps, and for each one of the like leaves, because we will define leaves like, as you said, like the entropy 0 because it's like 100%. Is there like cases that we get to all the leaves as entropy 0, which will show we got to the leaves, but we still have attributes left?
Oh, you mean, for example, we have outlook sunny is entropy 0.
Yeah.
So for example, whenever the outlook is sunny, let's say with the humidity because it has less attributes. So we have humidity high, and for all the cases that humidity is high, we say we go to like if they belong to class yes, and for all of them that humidity is normal, they all belong to class, for example, no. And we reach to the leaf, we still have some attributes.
No, like since we like get to the leaves, is it like does it mean that the
Because
attribute
we-
doesn't like help us to get to the like the decision, and we could have like ignored it from the start, or like how is it like can we let them like leave them as it is?
If I understood your question correctly, so we have several subtrees inside the tree, right? So for example, now this could be one of our subtrees. If we are at the like situation of selecting the best root node, so that situation that caused to entropy 0.
No. For example, like we have humidity, outlook, wind, and temperature here. For example, we went through like 3 nodes already, and we're like doing it step by step. So for example, we did humidity, like branches, outlook branch, and wind branch. But for example, in some case, we get to like the leaves as like entropy 0 after like we went only like through these 3, but the temperature still remain. So and there's like nowhere else to like add or like consider temperature anymore.
Yeah, if we reach to the point that we covered all the instances, all the tuples. So if all the tuples, for example, we have no more tuples to classify, then we don't need like further. If, for example, we already classified all the tuples using, let's say, 3 out of 4 attributes, then we don't need to use the other attribute at all.
Just a quick question on edge case. So let's say the gain for outlook and humidity are the same. Would you just simply go on to the next stage and then calculate another category and see which gain is higher, or if the gain of outlook and humidity are the same?
Yeah.
So we just go on to like calculate the edge or the gain of wind.
So for the information gain, I think it randomly select if you have like 2 similar information gain, it just randomly selects one. Yeah. And so now we reach to the point that we know the outlook, for example, is the root node, and we want to see what's next. So if the outlook is sunny, do we reach to the leaf node or not? When do we reach to the leaf node? when all the instances belong to the same class, or we have no more, for example, instances, we have no more attributes. So these latter two cases that are not the case because we already have more tuples and we already have more attributes. So we didn't reach to that point. But all the instances belong to the same class, yes or no? No. Because in Outlook Sunny, some of them are yes, some of them are no. Now, which attribute? So the question is, which attribute should be tested here? So if we started with the Outlook, and now here we reach to the lift with the overcast, because they all, it was homogeneous and all classes, all instances had the same class label. But for these two, now, should I put humidity here, wind here, or temperature here? So that's the next question, right? Now we do the same here. So we again have to calculate the entropy for all of the remaining features with respect to this one that we selected. So for example, let's say if I want to put after humidity, if I want to, we have sunny, humidity, temperature, wind. Okay, so after the Outlook Sunny, we have humidity, temperature, and wind. So what we should do, the same process that we did at the beginning, we calculated the entropy and information gain for all the attributes, we repeat it. Now with respect to the Outlook Sunny instead of the whole data set, right? Now we say, out of those instances that belong to class Sunny, let's calculate the gain of S Sunny. So here is not the whole set, but this just subset, right? We find the gain of S Sunny with respect to which attribute? For example, one time with respect to the humidity, then we calculate the gain of S Sunny with respect to the temperature and with respect to the wind. Now, after we selected the gain of this subset with respect to the remaining attributes, we select the one here whose information gain is the highest, right? And when you are calculating the information gain for each of them, you have to just make sure that you, so for example, S Sunny and humidity. So this is entropy of S Sunny. Right? Just be careful not to put the whole set here. So we deduct the entropy of S Sunny from the weighted sum of the entropies of S Sunny and humidity, for example, normal, S Sunny and humidity high, right? The weighted sum of, so here is the I to S of the entropies of the remaining features. So for example, you have to calculate the entropy of S Sunny with respect to temperature, for example, high or normal, humidity high or normal. So how many instances that we have when the outlook is sunny and humidity is high? So we are calculating the first one. So first of all, the entropy of S Sunny, we put the number there, which is 0.97. And then we have 5 instances that the S was sunny, right? Now 3 instances of sunny with humidity high and 2 instances of sunny with humidity normal. Now the entropy of, what is the entropy of S Sunny and humidity high? So what is the entropy of S Sunny and humidity high? Because here in in order to find the information gain of S sunny with respect to the attribute humidity, you need to wait to find these entropies, right? One of them is the entropy of S sunny humidity high. The other one is entropy of S sunny and humidity low. Oh, normal, sorry. So what is the entropy? So when you want to find the entropy, you have to check how many instances you have in each class, right? So what is the entropy of S sunny and humidity high?
Is it 0?
Yep. Why?
Because all of them play tennis is known for all.
Yeah. Yeah. So go back to the table. Now in the table, in your example, all the instances that the weather is sunny and the humidity is high, all of them belong to the same class, right? So entropy is 0. And how about the entropy of S sunny and humidity normal? Again 0, because all the instances. So we reached to that ideal split. Now we have like the purest in each of the branches. Now, for example, we did this for the humidity. We repeat the same process for temperature and wind. So, for example, in order to find the information gain of S sunny with respect to the attribute temperature, we have to calculate the entropies of temperature. What was the values of temperature? What are the distinct values of temperature? Hot, cool, mild. So you have to find the entropy of S for when the temperature is high. Then you have to find the entropy of S sunny when the temperature is cool, and then find the entropy of S sunny when the temperature is mild, right? And how about for the wind? So what are the values of wind? Weak and strong. So for weak and strong, so the gain, let's say the gain of S sunny and wind with respect to the attribute wind, what would be this one? So you have the entropy of S sunny. Now you have to find the entropies of weighted sum of all the values for the wind and deduct it from the entropy of the whole set, which in this case is S sunny. So what would be here? For here, you have to find the entropy of S sunny with respect to, so entropy of S sunny when wind is, for example, high, strong, yeah, wind is strong, or when the wind is weak, and you add that and you deduct the sum from the S sunny. So you want to see how this split of, for example, wind strong or wind weak affected the entropies. Is this clear? Okay. Now next move to, so this is just the remaining of the calculations until we reach to the leaves. So now, as I mentioned before, in order to see when we have to stop or when we understand when we reach to the node terminal or reach to the leaf, there are several situations. One of them is when all the instances belong to the same class. The other one is we finished all the tuples and there are no more instances to classify. Yes. When we have no more instances to classify, we declare that node as a leaf, and then we put, so what class label should be assigned to that node? The majority. Yeah. We look at the class labels and we put the majority there. And so this method, the problem with this method is that it's biased toward the number of values for an attribute. So what does that mean? So for example, consider an attribute day. In this example, we have 14 distinct values of day. this, with the formulas that the information gain has, because it perfectly classified each instance, so the entropy is 0, and then we have the highest information gain. Yep. So is it a good predictor? Is there a good predictor for to see whether we want to play tennis or not? No, it's not a good predictor, because if, for example, it's day 20, what do we want to, like, can we like go play tennis or not? So it's not a good predictor. But so this is just one problem with this. The same example is, for example, with the unique identifiers in each table. So if you, for example, choose a unique identifier, if you calculate the information gain for, let's say, if you have a table with the information of like customers, and then you have several features of customers to see whether, for example, they are going to buy something or not. If you calculate the information gain for the customer ID, because we have unique customer ID for each customer, then we have a large number of unique values for this feature. And this will result in a very high information gain, but the actual predictability or usefulness of this feature to predict is very low. So in order to address this issue, we can use gain ratio. So gain ratio is another method of selecting the best attribute. So we said that one of the issues in there were 3 issues. So one of them is how to select best attribute to a split. One was information gain. The other is gain ratio, or Gini Index. So these are the ones that we discussed. So we finished with the information gain. Now the gain ratio is almost the same as information gain. I'm going to answer you after. So it's the same. The only difference is that it's kind of normalizing in order to address that bias in information gain. Now it is trying to normalize that formula. So it is, the way that it works is that it penalizes those attributes, like, for example, the unique identifiers or the day in our example. So it's trying to penalize those attributes by using some form of like normalization. Now how does it normalize? It uses intrinsic information, or a split info. And let's see what is intrinsic info. Is the entropy of subset of the proportions. So for example, let's say we want to find the gain ratio of our set S with respect to attribute A. A could be outlook, wind, or whatever in our example. Now we calculate the gain, the information gain of S with respect to A. Now because the gain favor those attributes with high number of like distinct values and is biased towards them, we normalize it by dividing it to the split info, where a split info is the sum of, it's kind of an entropy with respect to that subset. So we are dividing to that in order to normalize it. So it's an entropy of our sub data proportions. So gain ratio, because of that split info that we have here, it prefers those splits that have partitions with higher or smaller than the other. We are dividing it by the split info, so we want to like penalize those attributes that have high distinct number of values. So it prefers the ones with the smaller partitions. Now, for example, let's calculate the gain ratio of our set S with respect to the attribute outlook. So first of all, we have to find the gain of S outlook, which we did before, and the number was 0.24 something. We calculated it before. Now the only thing for gain ratio, the only extra step that we have to do is that we have to find the split info, or that intrinsic information. So for the split info, we just find the entropy with respect for that proportion. So what are the total number of instances here? We had 14, right? 14 days. And we have 5 instances in the sunny, 4 instances in the overcast, and 5 instances in the rainy, right? Now, in order to find the split info of S with respect to outlook, which is the entropy with respect to that subpartition, we say, okay, 5 out of 14 instance belongs to sunny, so we have the probability of an instance being in sunny. What is that? 5 to 14, right? We have 14 days, 5 of them are sunny, so the probability is 5/14. And multiply by log, and then we sum for all other branches. So for the rainy, for the overcast. Now we penalize that gain information value by dividing it to this number. So now you see that the gain ratio of S with respect to the value of outlook is 0.156. So it's a less number, right? So it reduced the gain ratio, information gain. So for your practice at home, I highly recommend that you do the same calculation for all these features. So finding the info or like the entropies for the outlook, temperature, humidity, and wind, find the information gain, find the split info, and also find the gain ratio. The same way that I did. Another method is the Gini Index, which is Gini Index is another measurement. It considers a binary split. And so for each attribute, it considers a binary split. And so we have 1 minus sigma PCI to the power of 2, which calculate the Gini impurity of S, our subset, with respect to the classes that can be measured. So what is CI here? The PCI is the probability of an instance belong to class CI. And because it's a binary split, right, we have I and J, and they should be mutually exclusive. So that's why we say I is not equal to J. And then it's going to calculate the probabilities in each of those sub-branches. And when selecting attributes using the Gini Index, we select the attribute that most reduce the impurity due to partitioning on A. So we select an attribute that have the minimum Gini Index or the maximum reduction in impurity. Because the goal is to reduce the impurity, right? And when we reduce the impurity, it increases the Gini Index. Okay, so this slide is duplicate. And so now look at this basic algorithm for decision tree. What is the problem here? Now think about when to terminating the recursive process in building the decision tree. We said that we declare a node terminal either when all tuples belong to the same class, which means that we branch out of the trees so much that we reach to the nodes, we reach to the leaves, right? Or for example, there are no more instances to classify, or there are no more attributes. So the problem is that these algorithms are perfectionist. So they try to perfectly predict the class labels. And because they are perfectionist and because they try to perfectly predict the class labels, they also capture the noises there, right? Because the data comes with noise and anomalies. And when it learns those noises very well, the problem is that then it becomes overfit and it cannot predict well or perform well on unseen data. So here is the overfitting problem. So we grow each branch of the tree just deeply enough to classify the training examples as perfectly as possible, because we want to reach to the point that all instances belong to the same class. So we just branch out more and more until we reach very deep. And so, as I mentioned, because the data contain noise, and we have the problem that the algorithm learned those noises very well, and as a consequence, it overfits. So one problem with the overfitting is that because your model learned your data very well on the training set, it learned the training data very well, now it cannot perform well on other data. So the generalizability is very less, like very low. So it suffers from like low generalizability. And here's a definition of overfitting. We say that, let's say we have the error of a model as H, and we have two types of error. We could have the error on the training set and the error on the whole data. And we say the model overfits if we have another model that performs poorer on the training data with respect to our model, but perform better in predicting unseen data compared to our model. So if our model is not best, or there are some other models that predict better on an unseen data, on the test data, then we say that our model overfits, because our model only performs well on the training data. Now here, consider accuracy as 1 minus error rate. So as the error rate increase, the accuracy decrease, right? Now, now see the relationship between the size of the tree with respect to the accuracy, and we have the accuracy for the training data and on the test data. So for the training data, more node that we use, what will happen with the accuracy? The accuracy is higher because it is learning our training data very well. So the accuracy is getting higher and higher. So it is sensitive. Now our model is sensitive to every nuances on the data, so that it can predict like everything on the training data. But how about like on the test data? So now the model got so complex that it doesn't perform well on the test data. So when we increase the number of nodes after a certain point, so the accuracy on the test data increased, but up to a certain point, and after that it just decreased. Now the one solution is like that's why we do tree pruning. We have two main approaches for tree pruning. Does anyone know what does tree pruning means?
So it's essentially removing unused nodes, or like nodes that don't really help us.
Yeah, so not all nodes are very helpful. So instead of like growing a trees very deep and reaching to some like sub-trees that containing nodes that don't actually have significant like predictive strength, predictive power, or they contain anomalies, contain bias, or for example outliers, we can actually remove them. So there are two main approaches to do the tree pruning. We can do the pre-pruning or post-pruning. Before explaining that, here are the benefits of pruning. So we said that in order to address the overfitting problem, we use the pruning. How does it do that? We said that when the tree grows, when we have lots of nodes, so we have also more noise in the data, and some of our branches contain noise. So by removing those noises, and the overfitting problems when our model learned those noises very well, right? So we remove those branches with the noises, and to address the overfitting problem. It also reduced the complexity because we remove some nodes and leaves, and our tree become more simple. And because of its less complexity, because it's simpler, so it is more generalizable and also it's more interpretable. If you have, it's much easier for anyone to understand a tree that is more simple with fewer nodes compared to like a very complex deep tree. Now, one method is the pre-pruning, is that we, in the pre-pruning, we say, okay, stop growing the tree further when when your data split is not statistically significant. There are several ways to measure that. So, for example, you can put a threshold and say, okay, I don't want to go like, I set a threshold for example, maximum depth of my tree. So I don't want to go like deeper than a specific number, okay? So you put a threshold on, for example, the depth of your tree. And for example, another is to put a threshold on the minimum number of examples at each node. So if you are growing your trees a lot so that each node contains very few instances, like for example, why we said that the customer ID or for example, day in that table, our example, are not good predictors because they were very specific. They were they got like all the details. So for each day we had only one tuple and it perfectly predicted. So we can also put the minimum number of instances for each node and say, okay, if it gets less, stop growing the tree further. Now the problem here, there are several other ways to also do that. So here are just two examples that I mentioned. You can not only for the minimum number of examples, we can also put a threshold for the minimum information gain. So if we reach to the point that the information gain using a split is less than a threshold, so we stop it because there's not enough information gain. And so the problem is that it's hard to set a threshold. So what number? So for example, if I say I don't want to go deeper than some point, so how deep? So what is the maximum depth of my tree? Or for example, the other problem is that either your trees become oversimplified or with very less complexity. So if you have a high threshold, if you set the threshold too high, what does it to your tree? Like, is it oversimplifying your trees or like just very less simplicity?
Well, like, you're not really doing anything if your threshold is too high, right? Like you're essentially gonna get like still an overfitting tree.
Yeah, and it caused to become like your tree to be very oversimplified. And if we put a very low threshold, then it's very little simplification and it gets complex. Now, a better approach, like most of the time in practice, this method is better, is post-pruning, which we grow the full tree. So that is why we call it post-pruning. And we allow it to like get bias and have like overfit the data. And then we remove some of the stop trees. And how do we remove those stop trees is again based on several methods. And this is more successful in practice. So the post-pruning is especially useful when any individual feature is not informative, but like a combination of features are more informative. And so here are some methods to do the post-pruning. So here are just some functions. We can use the reduced error, error complexity, pessimistic error, and several others. So here I just covered like 3 of them. And for the reduced error pruning, what you do is that you just prune your node, like you grow the tree because it's a post-pruning method. So you are splitting your training data into a grown data, the grown set and pruning set. So you have 2 sets of data. And now you are going to compare the accuracy on the prune set with respect to when it is unpruned, right? And then greedily remove the one whose removal most reduced the error on the pruning set. So if you compare that accuracy between the prune set and the unpruned tree, when the removal caused the highest reduction in the error rate, means that higher accuracy, and then we can remove the one which most reduced the error on the pruning set. So another one is error complexity pruning. This one is very similar to the previous one. It starts from the bottom of the tree, and now for each of the internal node, it computes the cost complexity of the subtree. And for the cost complexity, in order to calculate that, it considers two factors. It considers the classification error of the tree, which we already had before, but it also considers the number of leaf nodes in the tree. So it's considering not only the classification error, but also the number of nodes. So it computes the cost complexity of the subtree at node n, and then it computes the cost complexity of the subtree at n if we prune it. That is, we replaced it with a leaf node, and then we compare the two values. If the pruning the subtree at node n result in a smaller cost complexity, we say that, okay, the subtree is pruned. And otherwise, we just keep it. So the only difference here is that it not only considers the classification error rate, but also considers the number of nodes. And finally, the last one is the pessimistic error pruning. So you know that when you are working on your training data, most of the time the learning algorithm is very optimistic. And so in order to penalize that, we can use a pessimistic error pruning. So if you calculate the accuracy on your training data, what would be the result? Is it very reliable? No, because it's when you're like just considering the accuracy on your training data, it's biased and it's very optimistic. So just to address that, we can use the pessimistic error pruning, and this method doesn't require a separate pruning set. So in all the other ones, we said, okay, we have a grown set, we had a prune set, and then we compared, for example, the accuracy or the error rate of the pruned set with the whole set, with the unpruned tree, and then we decided to either prune or keep. And here, the pessimistic method adjusts this error rate by just adding a penalty, and you see it in the formula that we just add some penalties to the error rate using on the training data. And the advantage is that it's fast, so no need to separate the growing and pruning set. That's why it is faster than the other methods. And here are some other issues in decision tree learning, like, for example, converting the decision trees to set of rules, which is very easy. How to deal with continuous attributes, I will talk about it in the next session, and then we start the hands-on. And how to scale up decision tree learning and other approaches that we don't cover. So we just covered the first three issues. So in order to convert a decision tree to set of rules, it's very easy. You start from the top, from the root node, and just move in each branch until you reach the leaf. For example, you say, if the outlook is sunny, and then you go on to the left branch and say, okay, if the outlook is sunny and the humidity is high, then the class is no, right? What if the outlook is, for example, rainy and the wind is weak? Yes. So this is how you convert decision trees to set of rules. So that one is very easy. Now, how to deal with the continuous attributes? We have two ways. We can use discretization. We had this before. Discretization, if we used it when you had like a continuous variable and you wanted to like convert it to like intervals, or convert it to a categorical feature. So for example, you had age numbers and then you converted it to like age ranges. So that was a discretization, right? And then we can use that interval labels instead of the actual data values. So for example, we can use the age between 10 to 20 years old instead of like age 10, 11, 12, 13, so on. And another way is dynamic discretization, which we dynamically split the value ranges into two sub-ranges during the tree learning process. And I'm going to explain the dynamic discretization next week. So we finish here. And there are just a few slides for the decision tree. And next week, bring your laptops. And we try to just have hands-on on example doing data pre-processing and then applying the decision trees, pruning, and everything that we have learned. Have a good day.